Welcome back to differential equations. In this video, we're going to be looking at a family of techniques known collectively as change of variables methods. The idea here is that if you can change the form of either the independent variable or the dependent variable, very often you can take a more complicated equation and turn it into something simpler. In this video, I'm just going to focus on the idea of if you know a substitution to make, if you know a change of variables that could be useful, how does it work? How do you use that to simplify the expression? In future videos, we will look at a couple of particular cases and ideas on how and why you might predict to make a specific change in variables. So let me get my head out of the way and let's jump into the first example. Here I have the differential equation y double prime as a function of t minus 2 times t times y prime of t squared equals 0. This is a second order nonlinear differential equation. Having just said that I wasn't going to focus on why I might make a substitution or why I might realize to make a substitution, I will point that out in this one. Although again, spotting this is not necessarily the idea. Being able to work with it once you are shown what could work is the idea. I'm going to make the substitution, let u of t equal y prime of t. So in this case, I am changing the function that I'm working on. And the reason that that is a powerful technique in this particular case is that my differential equation has y prime and y double prime, but not y itself. And the fact that that other function is missing will allow us to simplify quite a bit here. If I differentiate both sides of this definition, u prime of t is simply y double prime of t. That's pretty convenient. So we can substitute in, and we get that u prime minus 2t u squared is equal to 0. Now we have taken this second order differential equation and rewritten it as a first order equation. Not only that, but this first order equation is separable. I can rewrite it as u prime over u squared is equal to 2t. Then, integrating, I get that the integral of du over u squared is equal to the integral of 2t dt. It's been a while since we've talked about separable differential equations. Remember that the trick here is that I'm using a substitution. It's a little bit weird calling it a u substitution when the variable is already u, but u prime dt is the same thing as du. And with that, my dependent variable u of t turns into my independent variable u, and I can continue from there pretty nicely. I have a constant of integration here, which we usually write as c. In this case, I'm going to do something a little bit different and write it as a squared. It's still just an arbitrary constant. The reason that I want to do that is going to become apparent a little bit later on. Secret of mathematics. Very often, a mathematician goes through, solves the problem, realizes that their life would have been made a lot easier if they had named something slightly differently. So they go back, they just edit it, fix it, and pretend like it's been like that all along. That's basically what happened here. This would be a lot easier if I had that written as a squared instead of c. So let's just write it as a squared. Nothing's stopping us. But I'm not done here because this gave me u. I'm looking for y. And of course, I came up with u in the first place by saying that u is equal to y prime. So by substitution, y prime must be negative 1 over t squared plus a squared. And this is a directly integrable differential equation. Y is equal to the integral of negative dt over t squared plus a squared. That's not exactly an everyday use kind of integral, but it is actually a canonical form. That is the generic form of the arctangent integral. So y of t is going to be, the negative just hangs around. I have 1 over a times the arctangent of t over a, and then plus a new constant of integration. I'll call this one c. And again, knowing that I ended up here, at this point when I was looking at this integral and trying to figure out what to do, this is when I realized that calling that first constant a squared would make my life a lot easier. So I just very happily went back and did it. That's a very common way of going about things. All right, let's take a look at another example. X squared times y double prime, this time a function of x, plus 6x y prime of x plus 4 y of x is equal to 0. In this situation, it's a lot less obvious why I'm going to want to do this, but it turns out that an equation in this form can always be solved by a change of variables. Let x of t equals e to the t. So in this case, I'm rewriting my independent variable x, not my dependent variable. And I needed to change my function as well. In order to indicate that this is a different function, I'm going to put a bar on it. In other aspects, I might have put a star or something like that, but a star is going to get in the way because of the primes. So I'm going to put a bar on this thing just to indicate it's a slightly different meaning. Y bar is going to be a function of t, and it's defined as y of x of t. So it's not really a different function. I'm just suppressing and combining together the excuse me, sorry about that. I'm combining the function composition into one thing, and having this written as y bar is going to help me out because it will remind me that y bar prime is taking a derivative with respect to t. So that's going to be y prime of x of t, following the chain rule, has to then be multiplied by x prime of t. Conveniently, though, this is an exponential function, so x prime of t is also equal to e to the t, which is just x of t. So y bar prime is y prime times x. And then when I want to take y bar double prime, now I have to use the product rule and the chain rule. The derivative of y prime of t is going to be y double prime of x of t times the derivative of the argument x prime of t, and then I can leave y prime alone and take the derivative of x of t, x prime of t. But of course, x prime is just x, so I actually have x squared y double prime plus xy here. And that's a bit of a mess, but if I go back to my original differential equation, I can rearrange to take advantage of these new definitions. Remember my original differential equation just off the screen, probably just at the top of your page where you can still see it, x squared y double prime plus 6xy prime plus 4y is equal to 0. And I need to get x squared y double prime plus xy. Sorry, that should be xy prime. I lost that prime. I think I just didn't register when I was writing it on the touch screen here. But that's easy enough to do because I can take this 6xy prime and I can separate out one of them from the other 5. I just took what I had and made it a little bit more complicated because now it's a direct substitution. I have x squared y double prime plus xy prime, which is exactly y bar double prime. I have 5xy prime, which is exactly 5 times y bar prime. And I have 4y, which is the same thing as 4y prime, 4y bar, right? Y and y bar itself didn't change. The only thing that changed is I'm now talking about it as a function of t. And by performing this set of substitutions, I have taken my differential equation, which didn't have constant coefficients before, and I've rewritten it as something that does have constant coefficients, so I can solve this using the method of characteristics. It's been a little while since we've talked about the characteristic equation, but that's going to just give me xc squared plus 5xc plus 4 is equal to 0. That is factorable. It solves really nicely. Xc plus 4 times xc plus 1, which means that xc itself is -4 or -1, which gives me that y bar of t is some constant c1 times e to the -4t plus some other constant c2 times e to the -1t. And it feels like we're done because I've now solved for y as a function of t. Except that in my original differential equation, y was not a function of t, y was a function of x. And I created t by defining that x of t is equal to e to the t. Now, whenever you change the independent variable in a differential equation, or in any equation, in order for things to work, you have to choose an invertible function. X of t is e to the t. Rearranging that, solving x equals e to the t for t, gives me that t as a function of x is the natural log of x, right? The inverse of e to the t. And so I can write just like y bar of t is y of x of t. Excuse me. Just like y bar of t is y of x of t, I can also say that y of x is y bar of t of x because the choice of x of t is an invertible function. So I need y of x, just replace t with natural log of x. And technically I'm done, but this is something that's pretty easy to clean up using properties of logarithms. Multiplying in front of a logarithm turns into an exponent inside. -4 natural log of x is natural log of x to the -4, and then natural log of x to the -1 on the second term. Then from there, I have an exponential and a natural log, the exponential of the natural log of a thing. Exponentials and natural logs are inverse functions. They cancel each other out, leaving me with just the argument. So C1 times x to the -4, C2 x to the -1. So two very different approaches, two very different things that can happen in the approach of a change of variables. Here's one I'd like you to try. Y prime of t is equal to 4t minus y of t all to the fourth power plus 4. Again, I don't necessarily expect you to come up with the substitution on your own, but this is one that I think is fairly obvious in hindsight. If we let u of t equal 4t minus y, this should clean up and become a lot easier to work with than what it was before. So I'd like you to take a couple of minutes, work through solving this, see where you end up, and I'll see you in the next video.